Hello, my name is JMcCulloch, and this is KI5. So the basic overview is we have a signal coming into our antenna, going into the duplexer. The duplexer, all it is differentiating between transmission and receiver. The first mixer is an intermediate frequency. You use this to step. Instead of going from, call it 3 kilohertz up to 900, you do intermediate steps. It's a little bit easier on the whole system. That system is going into an amplifier, which is amplifying. It's a low noise amplifier. You want the signal to noise ratio to increase before it goes into the second mixer. You want a higher signal to noise ratio because if you're amplifying everything, you're not able to pick out the signal that you want as easily. So the second mixer is what takes it to the actual carrier frequency. And in our case, since we're demodulating it, we're multiplying it against another carrier frequency, which is shifting, giving us multiple copies. And one of those copies is going to be back at the frequency that we're looking for. So this is going into the demodulator, which is then fed into the digital analog converter, which is then used to do various things, whether that's voice going to the microphone, or that's a text message getting sent to your screen, etc. So the carrier frequency is the quickly oscillating signal on the top, and the modulating sine wave is your voice. So my voice right now is oscillating as a sine wave. Those two are multiplied together to create an amplitude modulated signal. So there's also frequency modulation, and cell phones use a combination of the two. Right now we're just going to focus on the amplitude. So in the frequency domain on the bottom left, we see there is a baseband signal, the wider one close to 0. And then you have the carrier frequency, which is the one spike later on. Those two, when they're multiplied, the baseband, again, like I said earlier, is copied around the carrier frequency. And a super simple diagram of that is the top right with the two frequency Fs around 0. So as we're demodulating, we now have this baseband that is centered around the carrier. If we multiply by another carrier, that carrier is doubled. Well, it's multiplied again, and you get a copy that's going to be back near the baseband. And the information that we want is now back where we need it, and then we use a series of filters to get the information that we want. This is a representation of how different frequencies are combined. On the left side, you see the frequency axis, and the sine waves are being produced and then combined. And from a time domain visualization, you see on the bottom right, that's where you get a lot of the noise, and we have to try to figure out how to differentiate between which signals we want. And that's where filters come in. And from a 332 perspective, cell phones are insanely complex, right? So these are just all the components inside of the cell phone. What we're worried about is the receiver processor, third down on the right, and the crystal oscillator directly below that, which is what's actually oscillating to create the frequency that we need, and the receiver local oscillator, which has to be matched with the transmitter local oscillator so that we can properly demodulate our signal. There's a bunch of other things there, but we're not going to really worry about that. So the most basic frequency local oscillator is just an LC circuit. And as the capacitor is charged, the energy from the inductor is pulled from it when the switch is closed to it. We're just charging the capacitor right now with that switch in the position it is. If the switch goes to 2, the capacitor is going to discharge until the inductor is charged, and then the inductor is going to discharge, and they're going to bounce back and forth. And the frequency at which they do that is what creates the local oscillations, which is what we use to call our carrier frequency. So this is a basic spectrum analyzer, and the spikes are the signals that we want, right? And the diagram on the right is a low noise amplifier. And that's the thing I was talking about, where we want to increase those main spikes that we have at 5, 15, 25, 35, 45 megahertz, and we want to ignore all of the base level noise oscillations. And as you can see, we use a complex series of inductors, capacitors, and transistors to do this. This is also, several of these transistors are what are actually amplifying the signal. From a 342 perspective, we have a ton of different frequencies that we can use for radio communications. But the ones that we're worried about are in the cellular range, specifically for GSM, is going to be between 900 megahertz to 1.8 gigahertz. And as we can see here, that's going to be anywhere between probably about 50 centimeters down to probably about 8 or 9 at the very small end. So we're dealing with very small wavelengths, which is why which is one of the reasons why we actually use the carrier frequency, so that we don't have to use these massive antennas. Because as we can see, if we're using 300 to 3000 hertz, we're at 10 to the second kilometers. That's a lot. That's a massive antenna that we would have to use. So we use the carrier frequencies to better send out the information. As far as the actual radiation pattern of cell phones, this is a very simple visualization of the far field radiation pattern. There's also a near field, but we won't discuss that. And then you also have to take into account, in every single circuit, anywhere that you have current flowing, you also have magnetic fields, and that's going to affect your noise a lot. So you have to be cognizant of that. And that's the end of my video. Thank you.